So we are live. Welcome to today's session of the Discrete Maths 2 course. Today's course session is going to be a game of two halves, like all the other course sessions, but this time even more so, because the first part is going to be devoted to completing our part of the course devoted to topics in the theory of computation. We will wind up our discussion of the cardinality of infinite sets. And we will have a very brief introduction to one of the fundamental results in the theory of computation, which dates back to around 1936, when Alan Turing proved once and for all that the halting problem is an unsolvable algorithmic problem. After the break, we will change mode. And we will start the part of the course that is devoted to all you ever wanted to know about the basics of linear algebra, but you never dared to ask. Just to quote from Woody Allen. Okay, so let's start. As usual, we are going to start by warming up, by answering a couple of questions. And this time, the couple of questions are on a slide that Dr. X produced the other day. And these questions, there are two of them, they have to do with cardinality. So Dr. X asks, can you convince me that the intervals 0, 1 and 0, 2 of the real line have the same cardinality? Now, what does this mean? This means the collection of all the real numbers between 0 and 1. This is the collection of all the real numbers between 0 and 2. Now, for those of you who have been at the previous lecture or have looked at the material or have listened to the lectures, this should not sound too strange. For those of you who haven't, this will look very odd. Why? Because 0, 1 is a proper subset, is strictly included in 0, 2. However, these are infinite sets, so the fact that one is strictly included into the other doesn't mean that they don't have the same number of elements. In fact, they do, and Dr. X asks us to prove it for him. So there we are. Scratchpad, like all the people at home are doing right now, they're taking out their pens and papers, and they're starting to write down what we are supposed to do. If they are not, they should be doing that. So here we have these two sets. The set of all the real numbers between 0 and 1, and the set of all the real numbers between 0 and 2. We want to argue that they have the same cardinality, that they have the same number of elements. How do we do it? Okay, in order to answer this question, we need to recall what it takes when two sets have the same cardinality. What it takes for two sets to have the same cardinality. And this has something to do with functions of a certain type between these two sets. What functions are we looking for? We are looking for a bijective correspondence, as your friend up there is saying. So we are looking for a function, h, between these two sets, which is a bijection. What does this mean? This means that if you feed it with two numbers which are different, it will spit out different results. That's injection. The second property that a bijection should have is that it should also be surjective. What does this mean? This means that no matter what number between 0 and 2 you pick, there always is some number between 0 and 1 such that h of a is equal to b. In other words, if you think of the function h as throwing darts, no matter what point in the target, the interval 0, 2 you think of, there is always a dart that hits it, and the function h directs the dart. Fantastic. So what would be a good definition for this function h? Okay, there is a subliminal message in the form that these two intervals take. One of them goes from 0 to 1. The other one goes from 0 to 2. So where do you think it's a good idea for H to map the point 1? To 2, yeah? So which means we double the number 1 to get 2. Of course, it doesn't have to be that way, but your colleague up there is saying, why don't we do it for every starting point? We double it. So we take the function that says, give me an x, I'll return 2 of x. First of all, this is actually a function between 0, 1 and 0, 2. Why? Because if your input number is between 0 and 1, your output number is going to be between 0 and 2, because you double it. Moreover, it's injective. Why? Because if you have that 2x is equal to 2y, then what is the relationship between x and y? Well, they are half. X is half of 2x, which is the same as 2y, so x is the same as y. That function is injective. So far, so good. Is it surjective? Yeah, suppose I want to get the point B in the interval 0, 2. What is the argument that I should plug into into H in order to get B as an output? Well, H doubles the input. So if you want to get B, you feed H with half of B. So the function is surjective. And note that if B is between 0 and 2, half of it is between 0 and 1. So everything matches. This function here is a bijection. Since your colleagues in the room have established a bijection between the interval 0, 1 of the real line and the interval 0, 2 of the real line, the two sets, the two intervals, have the same number of elements. Even though actually one looks much smaller than the other one. They're not smaller. One is just included in the other one, but it doesn't mean that they are not the same in terms of cardinality, in terms of size. Of course, this doesn't work over finite sets, because if I have 1 million kroner, you have 2 million kroner, you have more kroner than I have. You have more one kroner than I do. But if we had infinite collection of kroner, then, well, all of a sudden this would disappear. We would be equally rich. If you have as many kroner as points in the interval 0, 1, and I have as many kroner as points in the interval 0, 2, then we have the same amount of money. Of course, it's all predicated on an uncountable, on an infinite amount of money. It doesn't exist. Well, perhaps unless you're a banker, I guess, but that's another matter. We are not. We are doing science here, or trying to. Okay, so that's the first question. Here's another question from Dr. X. Again, we are dealing with intervals of the real line. And just for the fun of it, let me introduce you to a notation that I already introduced last time around. This is the interval that contains 0. It contains all the numbers from 0 to 1, but 1 is excluded. It's an open interval on one side. So all the real numbers between 0 and 1 excluded. Okay? This set here instead is the Cartesian product of these two sets, of real numbers. So its elements will be what? Now I know Cartesian product belongs to an earlier life, but let's bring it back. Let's resuscitate this earlier life. Whenever you have a set and you cross product it with another set, what are the elements of the cross product? They are pairs. I'm sure the people at home are screaming like the people here in the audience. I needed to sort of put my hands on my ears because they were about to fall off because of the noise that they were making here. These are pairs of real numbers in this interval. Now, Dr. X wants to know whether these two sets have the same cardinality. So what do we need to do to show that these two sets have the same cardinality? Well, they have, actually. So I'm giving you the answer. It's positive, but we want to be convinced. We are like St. Thomas. He has to see to believe. So what is it that I need to see to believe that these two sets have the same cardinality? A bijection between the two sets. Fantastic. But I want to make your life easier. Remember, at the end of the previous lecture, I told you that there is a theorem proved by Cantor, Schroeder, Bernstein that says that instead of exhibiting a bijection between these two sets, it's sufficient to exhibit two injections, two injective functions, one from 0, 1 to pairs 0, 1 of points in the interval 0, 1, and one going back from pairs to points. Sometimes this is easier than establishing a bijection. So let's try to use this method now. Okay, so now we want to have two functions. Give me an f, give me a g. Let's do some cheerleading here. Okay, the function f should be an injection that goes from the interval 0, 1 to pairs of points in the interval 0, 1. The function g should go the other way around, and it should also be an injection. Okay, give me an f. Okay, you want to take a point in the interval 0, 1, and you want to spit out somehow univocally determined point, sort of pair of points. Okay, so what does f does to a point in the interval 0, 1? It wants to spit out a pair of points now. And I mean, I say always spit out, just, but anyway, so you know, functions are very polite. They don't spit out. They just output, produce a result. But sort of spit out sounds good every now and then. Okay? So how would you do it? What if I tell you the second argument really doesn't matter in the pair? The second component of the pair, you can set it the way you like. So I set it to 0. So what should the first component in the pair be? X. Yoo-hoo! X, 0 is a pair of points in the interval 0, 1. And this function is injective because if you feed it with two different arguments, it will give you two different pairs. If x is different from y, then x0 is different as a pair from y0. Why? Because two pairs are the same if they are component-wise equal. This is nothing but an array of size 2. Two arrays of size 2 are equal if they hold the same elements, point-wise. The first entry is the same, the second is the same. But if the first entry is the same, then x is equal to y. If you have x0, y0, then x is equal to y. So the function is injected. Is that okay? So far, so good? If not, well, think about it at home. I was about to say scream, but I've already heard too many screams for the first 5 seconds. Okay? Any doubt about this? Because now you need to do the cool stuff for me. Give me a G. Okay? So I'll make your life a little bit easier. Now, a point in the interval 0, 1, 1 excluded, is going to be something that looks like this. The infinite decimal expansion. And another point in that interval is going to be something that looks like that. An infinite decimal expansion. Now, what I want you to do is to take these 2 points, these 2 infinite decimals, and out of them, construct a single number that is uniquely determined by the 2 numbers that you get as input. And I have one word for you: a round-robin interleaving. Give me an A. Give me a B. Give me an A. Give me a B. Give me an A. Give me a B. And I stop here because otherwise I spend the whole lecture doing that. And more, because that's an infinite decimal. Okay, so what is the thing going to be like? 0 point what? A1, followed by B1, followed by A2, followed by B2, followed by A3, followed by B3, and here we stop because you can go on to infinity if you wanted to, and if you had enough time, which you don't. Sorry. Okay, so there you are. This is a function that takes 2 real numbers in the interval 0, 1, and out of them construct a real number in the interval 0, 1. Moreover, this real number is uniquely determined by the 2 real numbers that you put as argument. Why? Because if you put 2 different numbers, the output is going to be different, because of the way you constructed this. And you can argue about this at home. So this thing is an injection. An injection. And this other thing is also an injection. So, by the Cantor-Schroeder-Bernstein theorem, there is a bijection between the 2 of them. We don't need to build it. We know it exists. In fact, we have already used this method of the interleaving method in our previous lecture, and to argue that the integers were as many as the natural numbers. We said, okay, I start from 0, plus 1, minus 1, plus 2, minus 2. And in that way, you enumerate all the integers and you put them in correspondence with the natural numbers. That's exactly the same method, which in operating systems is called round-robin scheduling. Now you know where it comes from. Not from operating systems, but from Cantor's work. Well, I'm sort of pulling your leg, but the idea is really the same. So far, so good?
I'm wondering if you take both the arguments, multiply them together, and then add argument all of them.
Okay, so I mean, I'm not claiming that this is the only way to do things. It's just the way that I think is the simplest of them all. But there may be other possibilities, which I encourage you to try at home. Excellent, I hope. So here are some other interesting things, or perhaps things that for deranged minds like mine are interesting. Some other interesting things about infinite sets. So suppose that you have a countably infinite set. When is a set countably infinite? When it can be put in correspondence with the natural numbers. Fantastic. So somebody gives you a countably infinite set that no matter what set is, any subset of this set, which is infinite, is going to be countably infinite. Why? Scratchpad. And of course, you at home should be thinking about this, beavering away at your own argument. So suppose I have a set A. Let's make it red because I had red set up. That's a countably infinite set. Okay, so what does this mean? It means, as your colleagues in the room told me, that this set can be put in correspondence with the natural numbers. Okay, so in particular, I can write this set as the first element, the second element, the third element, the fourth element, and so on. And that's really the implicit correspondence, the bijection between the natural numbers and this set. I can enumerate these elements. Now, let's assume that B is a subset of A, and it's infinite. What I want to argue is that this set here is also countably infinite. It can be put in correspondence. Its elements can be enumerated. Well, but intuitively, and now actually intuition does help, intuitively it must be the case that its element can be enumerated. Why? Because I could enumerate all the elements in A, and the elements in B are in there. B is a subset of A. So how do I do it? How do I do the enumeration? Well, I look at the enumeration of my set capital A, and I start traveling through it from the beginning onwards. I was about to say the beginning to the end, but there is no end. From the beginning onwards. I look at the first element, A0, and I ask myself, is it in B? If the answer is no, I move on. No. I ask, is A1 in there? If the answer is yes, I write A1. Then I ask, is A2 in there? The answer is no. Is A3 in there? If the answer is yes, I write it. And you can see that I can continue like this, enumerating all of the elements of B. And I never run out of them because B is infinite. So in this way, I enumerate all of the elements of B. That's why B is going to be countably infinite. Some other property. If A and B are countably infinite, then their union is going to be countably infinite. Why is that? Let's go back to our scratchpad paper and let's be wasteful with the paper. Okay, here I have A, countably infinite. So this means I can enumerate it. And here I have B. Let me use a different color. Otherwise, it looks like we are in a British phone booth, if they still exist. Okay, I can enumerate all the elements of B. Now, what I want you to do for me is to list all the elements of A union B. And you know, I have one word for you. You know what this word is? Sorry? Round robin, interleaving. So, you know, by now you're experts in this. You can write parallel programs like crazy. Okay, so that's how I do it. That's a B3. It doesn't really matter how I do it, but I want to stick to round robin that way. That's an enumeration of the elements in the set A union B. So this set is countably infinite, as we claimed. So basically, all the elements of A go in the odd positions, and all the elements of B go in the even positions of the enumeration. Now, doesn't this look suspiciously like Hilbert's hotel that I mentioned last time round? Think about it this way. A is our Hilbert hotel, infinitely many rooms, all full, filled with the elements of A. Now you got the infinite bus of elements of B coming along. We want to make room for them. So what is it that we do? Well, we'll create a gap in all the even positions in the sequence. So we let A0 stay in his room, but A1 goes to room 3, A2 goes to room 5, A3 goes to room 7. And then we have all the even numbered rooms, apart from free, for the elements of B. That's Hilbert's hotel at work, without the theater, or only with some of the theater. Great. It should be B2, yeah, it's absolutely. Your colleague is saying, I think it should be B2, absolutely. I wrote B3. Not that it really makes any difference, but I don't want to confuse you. I could have just written B2 afterwards, but absolutely. Now this looks like a thought. But anyway, it's a B. Fantastic. While I'm strutting my lack of skills here in writing on this thing, I'm giving you people the opportunity to think about what they're learning, or what they're teaching me, actually. So by not coming to the lecture, you're missing the opportunity of teaching me something. Okay, fantastic. But now you may say, okay, we used all this mumbo-jumbo about cardinality of sets to show that there are lots of real numbers out there that cannot be computed by an ideal computer with an unbounded amount of memory. So what? I don't care, because I really never wanted to write programs that that spit out the decimal expansion of real numbers. Are there natural algorithmic questions, whatever natural may mean, that our ideal computer cannot solve? And of course, you know that's a rhetorical question. The answer is yes. In fact, the answer is such a resounding yes that one can even argue that most of the natural algorithmic questions are unsolvable by means of our ideal computer, regardless of iPod, iPhones, and whatever else you may think about right now. Now, this question is a question that relates to a misconception. And this misconception is a natural one to have, because we use computers all the time to do lots of cool things. They can drive cars today. They can translate from one language to another. They can even recognize images. They can tell me that I'm making a mistake when I'm using the automata tutor. They can do all kinds of things. They can even tell me what mistake I'm making and what kind of language my automaton actually accepts instead of the right one. In 1984, the Time magazine ran a special issue on software. And the editor of a software magazine went on record as saying, put the right kind of software into a computer and it will do whatever you want it to. There may be limits to what you can do with the machines themselves, but there are no limits to what you can do with software. I have one word for this: bullshit. This is completely false. See Theory of Computation for details. What I'm showing you now is one example of one thing, and I mean not falling in love, not writing the next Hamlet. I'm talking about a well-defined algorithmic problem that machines cannot solve now and will never be able to solve. So what is this problem? This is something that goes under the name of the halting problem. Now, fix a programming language of your choice. C++, yeah, that's the one and only, isn't it? In fact, it's not the one and only, it's the only one you typically see, but then here at least. Okay, so let's write P for the source code of the program P. You mean the string that tells you what the program P is. It's a string. Let's assume that P only has one input, just for the sake of it. And P of X is the output that results from running the program P on input X. And let's assume that this program takes strings as input. Now you may say, okay, my programs take all kinds of inputs. But if you think about it, all kinds of inputs are represented as strings of bits. So your ultimate data type is strings of bits. That's the only data type, actually. All the rest is syntactic sugar, built on top of strings of bits. Inside here, there are only, where here means the machine that you're staring at home, there are only strings of bits if you go down to an appropriate level of abstraction. So assuming that your input is just a string of bits and only one, is no loss of generality whatsoever. Everything is a string of bits. Now, what is P fed with P? One of your colleagues is saying it's endless. Well, it depends. It depends. What this means is that we actually feed the program P with the string that describes the program. So we feed P on its own source code. You may think this is strange. It's not strange at all. A compiler in C++ can compile itself. So that's absolutely what this is. It runs on itself as input. Well, and this is really at the heart of computer science. It's self-reference. Now, let me issue the $1 billion, Icelandic kroner, challenge. I want you to write a program, let's call it halt, which has the following behavior. Whenever you feed it with the program P, it returns true if P holds on input P. And it returns false if P does not hold on input P. That's a termination checker. Wouldn't it be nice? It would be a very useful program because, I mean, you know, there are possibilities whenever you write recursive programs, for instance, like the ones that you're writing for this course or for many other courses, I guess, like data structures, it would be useful for you to know before you actually run the program, is it going to run forever on some given input? If the whole program tells you, yes, it's going to run forever, you don't run it. Otherwise, you do. Now, that's your software development task. And if you succeed, I'll give you $1 billion Icelandic kroner. But there is a small print. The small print says, if you fail, you give me 100,000. Okay? Now, I'm not Maria Montessori or Maria Teresa from Calcutta or anything like this. If I'm posing you this challenge, it's because you can't do it. So, for instance, if you write a program like this, that always terminates, it's not going to solve the halting problem. It might be the big picture solution, but it's not the right one. Because, for instance, it will return true when you feed it with a program that does, while true do nothing. And you can write these programs, can't you? Now, the fact that this program cannot exist in any programming language under the sky has been known since the 1930s. That's why it's important for you to know the history of your subject, so that if somebody asks you to write thing, you tell them, okay, sorry, I can't. Doesn't matter how much money you offer me for trying. Well, actually, the offer was not for trying. In that case, I would even accept. It was for succeeding, which is impossible. So I want to show you the proof of why this is impossible. there cannot be a program halt in any reasonable programming language that has this input-output behavior. Why do I want to show it to you? For two reasons. First of all, because it's not examinable material, so you can relax and appreciate it for the beauty of it. Second, because Turing did it, and he's one of my heroes. Well, I'll give you two reasons. We are in binary, so I'll give you a third reason. The third reason is because it's beautiful. Absolutely. And then you can sort of tell your friends about it. Because it's a one-line proof. Actually, let's make it three. It's a proof by contradiction. So breathe a sign of relief. I'll lead you through it step by step. So we are going to assume that there is this program halt with the given behavior. You give it a P, it will return true if P terminates on input P, false if P does not terminate on input P. So since somebody, for instance, a magic wizard, has given us this program halt that we assume exists, we can use it as a method in a larger program. Let's call this larger program confuse. Confuse takes an argument P, and it does something very simple. It calls halt on input P. That's absolutely legal because halt is a library program that we assume we have. Then halt returns a Boolean. If the Boolean is true, confuse loops forever. And instead of loop forever, write whatever loop forever program you like. While true, do nothing. Or while true, do increment X. If halt P returns false, then we take the else branch and we finish. Okay, in other words, we do exactly the opposite of what halt P does. Now, you agree with me, I hope, that if halt is a library program that I can call, confuse is a program. It's just if Boolean, then something, else something else. Okay? I'm not telling you how you implement this in your favorite programming language, but you can. And I'm not telling you how to implement return because you can. You terminate. So if halt is a program, confuse is a program. But then we can run confuse on its own source code. Because the source code of confuse is a string. Confuse is a program that takes a string as input, so we can run confuse on the source code for confuse. We run it on itself. And now a contradiction looms. Why? Because what is it that confuse can do on input confuse? If you're confused, it's not a problem. Look at it at home, because that's why this thing is called confuse anyway. So what does confuse on input confuse do? Well, if we look at the source code, there are two possible outputs here. It either loops forever or it returns. Okay, so let's see. When is it that it halts? It halts when it has taken the else branch. But it takes the else branch when halt of confuse returns false. But when is it that halt or confuse returns false? By definition of halt, this is exactly when confuse does not terminate on input confuse. So if confuse halts on input confuse, it will not terminate on input confuse. Okay, then perhaps actually confuse does not terminate on input confuse, but then it has taken the then branch here. And if it has taken the then branch, this means that halt of confuse has returned true. But then this means that confuse actually terminates on input confuse, because that's what halt does. It checks whether confuse terminates on input confuse. So, in other words, we've just argued that confuse run on itself, on its own source code, holds if and only if it doesn't. Ouch! That doesn't sound right, does it? That's a blatant contradiction. So what was the problem? Okay, the problem was everything we've done is legal. The only point which might be wrong is the fact that we assume that we had this library program that behaves like halt. If we have this library program, we can code confuse, and then we run into a deep shit. Excuse my French. Don't know why they say that, but this sounds good, especially if you're not French. Okay? So if we have halt, then we run into a deep, terrible hole of contradiction. So there must be something wrong with our assumption that we have halt, so halt cannot exist. Bingo. The halting problem is algorithmically unsolvable. Note, this means that it's not just algorithmically unsolvable on C++ on our current machines. It's algorithmically unsolvable no matter what programming language people will invent in the future, run on whatever machine, even with an unbounded amount of memory. So it's an impossibility result that is not for now, it's forever. Congratulations. You've seen your first unsolvable problem. So if somebody tells you computers can do everything, like the guy from the software magazine, just tell them, bullshit. For instance, they cannot solve the halting problem. For instance, they cannot check whether two arbitrary programs compute the same function. For instance, they cannot check if my program, when run on input 35, terminates or not. And lots of other stuff. So the good thing, the incredible thing, is not that we cannot solve everything using computers. The cool thing is that we can solve so many things using them. It cannot be everything, but it's a hell of a lot. So as James Brown, one of the early computer scientists, said, I'm a computer scientist, I'm proud. So you should. And on this word from James Brown, I close the first part of the course and the first part of this lecture. After the break, we will be talking about linear algebra. I know it's a put down, but we have to do it.